Yes. Actually, we have already discussed the first part of quantum mechanics. The first part was what is classical mechanics and what was the need of developing a new mechanics, which is quantum mechanics. Actually, as I have already discussed in the first part, that when the wave nature of electron was discovered, then it became essential to develop a new mechanics because classical mechanics was unable to deal with the energy of electron because in classical mechanics we have separate equation for wave and separate equation for particle, but electron has both particle and wave nature. So we needed a mechanics that can be used for a system possessing both particle and wave characteristic like electron. In the second part of quantum mechanics, we have classified quantum mechanics in two parts to make it less time consuming. In the second part, we have to discuss what is the fundamental equation of quantum mechanics and how to determine the energy of electron using quantum mechanics. And second, and also how to explain Heisenberg uncertainty principle on the basis of quantum mechanical uh, concept of system. So we are starting with the second part of the quantum mechanics, and that this starts from Schrödinger wave equation. This is the Schrödinger wave equation. Actually, Schrödinger, starting from the classical wave equation, he inserted the de Broglie equation in the classical wave equation and was able to derive this equation. Now you will see that in this equation you have mass. This mass is the characteristic of the particle. And you have also psi. You will see that psi is the property of wave. It is a wave function. So this is the property of particle. This is the property of wave. So both these characteristics are present in this equation. Therefore, this equation can be used for determining the electron energy of its electron or using both particle and wave nature. Now, in this equation, this is three-dimensional. This is three-dimensional equation, Schrödinger wave equation. Now, we have to differentiate psi with respect to x, differentiate psi again with respect to y, differentiate psi with respect to z. Differentiation has to be carried out twice. We have to differentiate psi with respect to x twice, keeping y and z constant. We have to differentiate psi with respect to y twice, keeping x and z constant. We will have to differentiate psi with respect to z, keeping x and y constant, and then we will have to add these three dx. And then this is 8 pi square by x squared into e minus p psi 0. We have to add this into this, and then we will get this equation will give you energy. Now here m is the mass of electron, and h is already h is Planck's constant. And pi is 27 by 3.14, and the h is length. This m is then next point is total energy of electron. Total energy of electron is the potential energy of electron. Now total energy is equal to kinetic energy plus potential energy. So this is kinetic energy plus potential energy minus potential energy. So E minus B will be kinetic energy of electron. And psi, which is a new thing, psi is most important. Psi, what is psi? Psi is the wave function of electron. Wave function of electron. What does it mean? Wave function means property. This is the characteristic of the wave. This is the characteristic of the wave nature of electron. Because electron has wave nature, therefore it must have a property that is concerned with the wave. Because psi is wave property. It is the electron has got this wave function because it is a wave. It is property of wave function. Actually, it is amplitude function of the particle wave. Amplitude function of the particle wave. Particle wave means the wave associated with the material particle. For that wave, it is amplitude function. That is, amplitude is this is wave motion, and this is the amplitude. This is the amplitude, the maximum displacement. Now, it is should be, it is needed to make it clear that psi is not amplitude. Don't think that it is amplitude of the wave. It is something that depends upon amplitude. It is a property of wave that depends upon amplitude. Amplitude is also property of wave. So it depends upon amplitude. So it is not an amplitude function. Actually, you'll see that psi is a kind of mathematical expression. For example, suppose that the electron is moving along the x-axis, and we say that psi is equal to 2 sine 4kx. Here k is a constant. Now, x is the displacement in the x-axis, along the x-axis. So as x changes, the psi will also change. So from this equation, this is the mathematical expression for psi. From this equation, you can calculate value of psi for different values of x. K is a constant, you know the value of k. So actually, wave function is a mathematical expression that describes the motion of the electron. The motion of the electron. Now, actually, the physical significance of psi, physical significance of psi, they say the Max Born in the year 1954 gave the physical significance of psi. Actually, for light, intensity of light is proportional to a square of amplitude. That is, the amplitude is doubled, the intensity will increase 4 times. And what is intensity? Is the number of photons falling at a point, at any moment. Using this equation, or in analogy of this equation, Max Born suggested that for electron wave, the probability of finding the electron at any point, this is equal to psi square. This is P is proportional to psi square. be the probability of finding the electron at any point in the space. P is actually F and psi squared into dx. This is the probability of finding the electron, within x and x plus dx, within x and x plus dx. Now, suppose we have now for this one, for giving the significance of psi, the Max Born was awarded Nobel Prize in the year 1934. Now let us suppose an electron, this is x-axis, and an electron is moving around the x-axis. And actually, there is a restriction. There is a restriction on the movement of electron. The restriction is, it is moving between two barriers. This is one barrier, this is second barrier. The distance between them is L. L is the distance between this. The barrier at this point, the potential energy is infinity. That is, if electron will come here, its potential energy will become infinity. And potential energy can't be infinity. That is, as electron will reach here, it will be repelled by infinite potential. So electron can't cross this barrier. Similarly, here also the potential energy of electron is infinity. That is, an infinite retarding force exists at this point, and it would repel back electron. So electron has no option but to always move within these two boundaries. Okay, this is known as electron in a box, in a one-dimensional box. Now, what will be the probability of finding the electron within this box? Now, calculate probability at each and every point. And then, because you know the value of psi, suppose psi is 2 sine 3kx. So as electron moves in the direction, the x changes. So put the value of x. You know the value of k is a constant. You can calculate psi at each and every point. And just square this psi squared. This will be probability. And if you add all these probabilities, the sum must be equal to 1, because 1 means the probability of finding the electron is 1 means electron must be somewhere within these two ones. Because the electron can't cross the 1, so it must be somewhere. So probability of finding the electron must be 1. This can be put as the integration psi square dx from 0 to L is equal to 1. If a wave function, this means if wave function is satisfying this equation, this means wave function is obeying the boundary conditions. Our boundary condition is that the position of electron can't be less than 0 or 0. The position of particle can't be greater than 0 or L. It must be in between 0 and L. This is the condition. So we have the psi square. Yes. Now, if a psi is satisfying this equation, psi is said to be normalized. Normalized. Psi is said to be normalized wave function. A wave function that satisfies this equation is known as normalized wave function. Okay? So normalized wave function. This is the Schrodinger equation, which is in 3 dimensions. Which is in 3 dimensions. For simplicity, for convenience, we are writing this equation in 1 dimension. In 1 dimension, this equation is d2 psi by dx squared plus 8 pi squared m h squared e minus v psi 0. This means electron is moving only along x-axis. Electron is moving only along x-axis. Now this equation can be, this is Schrodinger wave equation in 1 dimension. Now we have to see what is the basic equation of quantum mechanics. The basic equation of quantum mechanics is A psi equal to A psi. This is the basic equation. This means this A over what? Overhead is a inverted way. This is actually operator A. This is operator. Operator of some property. Actually, in quantum mechanics, for every observable property, like total energy, kinetic energy, potential energy, linear momentum, angular momentum, position. These are observable physical properties. Now for each of these, there is operator. For total energy, we have an operator. We have seen that in Schrodinger equation, you will get total energy operator. This is H actually. We have total energy operator H. We have for kinetic energy, we have operator. For potential energy, we have operator. For linear momentum, we have operator. For angular momentum, we have operator. For position, we have operator. So for every observable physical property, there corresponds an operator in quantum mechanics. And if wave function is operated upon by this operator, this is not multiple. Here it is not multiple. It is an operator. It may be differentiation. We have to differentiate this. If this psi is operated upon by this, you will get back psi again. The same psi will reappear. Multiplied by, here it is product, multiplied by a constant. A is constant, and A is the total value of this observable property whose operator has been used. Suppose we have used the operator of total energy, then A will be total energy of this system. If you have used kinetic energy operator, then A will be kinetic energy of the operator. If you have used potential operator of potential energy, then A will be potential energy of the operator. Okay. So when wave function is operated upon by A, when wave function is operated upon, here I am writing here, when wave function is operated upon by A, we get back psi again multiplied by a constant, multiplied by a constant A, which is energy of sorry, which is value of the property whose operator has been used, whose operator has been used. Actually, A is operator of any property and small a the value of that property. That property is the value of that property. Okay? A wave function that satisfies this equation. And satisfying means if psi is operated upon by this, you get psi again multiply a constant. If this comes to be same, comes to be true, then psi is said to be a eigenfunction. Psi is said to be eigenfunction. A psi, any psi that satisfies this equation is called eigenfunction. And the constant A, is called what? Is called eigenvalue. Eigenvalue of the property whose operator has been used. Whose operator has been used. So this is the basic equation of Schrodinger equation. This equation is like this. You can compare this. Suppose psi is farm. Agricultural land. Farm means agricultural land. Now, if you, in this form, if you sow the seed of paddy, you will get back same farm again. And plus what? The crop of paddy. If this operator is suppose this is seed of paddy, then A will be the grains paddy grain crop of paddy, and psi is the farm. So farm will remain as it is. If you sow the seed of say wheat into it, you get back same farm, and with the crop what? Crop of. So the same equation is here, that when psi is operated upon by any property, we get back psi again multiplied by a constant, and that constant is the value of that property. Okay. So this is the basic equation. Now, for Schrodinger wave equation is the same equation for energy. That is, this is the operator for energy. I am deriving the same equation. We are taking one dimensional Schrodinger equation so that it may be convenient, may be easy. So d2 psi by dx squared plus 8 pi squared m by h squared e minus v psi. This is 0. Correct? Now, this equation can be rearranged as d2 psi by dx squared. This is equal to minus 8 pi squared m by h squared e minus v psi. And if this quantity is brought this side, then you will get the equation like this, minus h squared by 8 pi squared m d2 psi by dx squared. This is e psi minus v psi. And if minus v psi is brought this side, then you'll get the equation minus h squared 8 pi squared m into d2 psi by dx squared plus v psi. This is equal to e psi. This is equal to e psi. Now, we can put this in this form, in operator form. This is minus h squared by 8 pi squared m d2 psi by dx squared plus v psi. This is v psi. Okay? And this is an operator. Let us denote this by h, capital H. H psi is equal to v psi. This is Schrodinger wave equation. Schrodinger wave equation in operator notation form. Here, H is, I think we have noted all those lines. Now I am just erasing them. Now this equation is S psi. Again, I am repeating this. S psi is psi. Where H is d2 H is minus h square minus h square 8 pi square m. This is d2 by dx square plus v. This is called Hamiltonian operator. Hamiltonian. What is operator? Operator is a mathematical symbol that gives you instruction about the mathematical operation to be performed on the wave function. To be performed on the function. That is called operator. So this is the operator. This gives the instruction. That what instruction? That differentiate psi with respect to x twice, then multiply this by this. And this is potential energy. Multiply potential energy with psi, and then add this result to this result. This is the entire operation. And this operation is called Hamiltonian operation. Hamiltonian operator. Hamiltonian means total energy. Total energy. So, what is Schrodinger wave equation? The Schrodinger wave equation states that when wave function psi is operated upon by Hamiltonian operator, we get back psi again multiplied by a constant. Here it is multiplied by a constant, and that constant is the total energy of the electron. When psi is operated, this equation states that when psi is operated upon by h, we get back psi again multiplied by a constant. Multiplied by a constant E, which is the total energy of electron. A wave function that satisfies this equation is called what? A wave function that satisfies this equation is called eigenfunction. And the constant A is called a constant E. Constant E is called energy eigenvalue. Energy eigenvalue. And this is called energy eigenfunction because it is energy equation. So this is Schrodinger equation, and this equation helps you to calculate total energy of electron by operating psi with H. Okay? Constant E is called energy eigenvalue. Now, we would like to see how energy can be calculated using this equation. And for this, I am giving you an example. By means of illustration, we will be able to explain this. The problem is an electron is moving along x-axis under force-free condition whose wave function, whose motion is described by the following equation. Following equation. Psi is equal to sine 2kx. Psi is equal to sine 2kx. The motion of electron along x-axis can be described by this equation. As the value of x will change, the wave function will change. And describing the wave function, you can calculate the probability of finding the electron at that point. K is a constant. Okay. Calculate energy of electron. Now see how we can calculate the energy. Okay. Now energy can be calculated by operating psi with H. H is the Hamiltonian operator. And what is H? H is minus H squared 8 pi squared m d2 by dx squared plus v into psi. Psi is what? Sine 2kx. Now, since electron is moving under force-free condition, so its potential energy will be zero. So its potential energy will be zero. The question, it is moving under force-free condition. This means no external force is acting on the electron. And since no external force is acting, so its potential energy will be zero. Potential energy always arises due to interaction with some external force. Okay. So V is zero, that is V is zero. Then this will be equal to S psi. This is equal to minus H squared 8 pi squared m d2 by dx squared into sine 2kx. V has been set equal to 0. Then this is equal to minus H squared by 8 pi squared m This is differentiation of sine 2kx with respect to 2kx will be cos 2kx. Cos 2kx as differentiation of 2kx with respect to k will be how much? Differentiation of 2kx with respect to k will be 2k. 2k. Now we have differentiated these once with respect to x. Now we have to differentiate second time d by dx. This is equal to minus h squared 8 pi square m. This is d by dx. 2k is constant, so just remove it. And cos 2kx. The differentiation of cos 2kx with respect to x will be minus sine 2kx. And differentiation of 2kx with respect to x will be 2k. So this will be into 2k. So this equation will be minus will be plus. This is h squared by 8 pi square m into 2 into 2, 4 k squared. And this is sine 2kx. What do we see? You see that the same wave function that was operated has come back. The same wave function has come back. Multiplied by a constant. This is constant. This is equal to E psi into psi. Psi is E is this. So E is 4k squared h squared by 8 pi squared m. 8 pi squared m. Now see, k is a constant, h is a constant, pi is a constant, mass of electron is a constant. So this is also a constant. Thus, we see that this equation is a eigenfunction, energy eigenfunction of electron. Because when this is operated by energy operator, we get back the same function again, multiplied by a constant, and that constant is the energy of the electron. This is the energy of the electron. Putting the value of k, h, pi, m, you know the value of k is a constant, h is also constant. We can calculate energy. This is how the energy can be calculated. Now, the next point is the explanation of Schrödinger wave equation. Explanation of Schrödinger wave equation on the basis of quantum mechanics. On the basis of quantum mechanics. Now see, suppose we have an electron whose wave function is given. Suppose this wave function is exponential a into exponential minus I kx. This is the wave function of electron. Now, since electrons wave function a is a constant, this a is not amplitude, it is normalization constant. You will have to normalize this like this. A exponential minus a, this a, remove this, a exponential I kx, and now just square it. Square this also, a pura died, and then into dx. Between, suppose 0 to L, if the electron is confined in this region. Now suppose the value of this is 4. Then a squared will be 4. Because the value of this is 4. So a squared is this is equal to 4 into a squared. This is the value of this is 4. So A will be 2 equal to. So you can find out the normalization constant A. By applying the boundary conditions, it is possible to calculate the normalization constant A. Okay. Now, so A is the normalization constant. Psi is this. We have the value of psi, and using this psi, you can calculate what? You can calculate the momentum of the electron. Because for a given wave function, the momentum will be different. The momentum will be certain, definite value. Now, because you know that momentum has also its operator. So if you operate this by momentum operator, if you operate this by momentum operator, you will get the value of momentum. Or if you operate this by energy operator, H, you will get what? The value of energy. So you can calculate energy. And now you have to determine position also. For determining the position, you have to what? We have to determine psi square, modulus psi square. This is the probability of finding the electron. This psi square, since psi is complex conjugate, so this will be equal to A into exponential minus ikx into A exponential plus ikx. And this is equal to A squared exponential 0, or anything power 0 means 1. So this is equal to A squared. Now, since A is a constant and there is no position variable x in this equation, so this means the probability, this is probability of finding the electron, the probability of finding the electron at each and every value of x, whatever may be. Suppose the electron is moving along x-axis, then at every point, the probability of finding the electron is constant, irrespective of the value of its position, irrespective of the value of x. This means the position of electron is uncertain. Electron is everywhere with same probability. This means the position of electron is uncertain. So we see that since wave function is given, so by operating this by angular momentum wave function, you can find out its momentum, or you can find out its energy by operating with Hamiltonian operator. But you can't determine its position. You can't say anything about the position, because then the position at each and every point will be constant, will be the same. This means the position will be totally uncertain. Again, suppose another case that we want to specify the position, and then we will see that what will happen to momentum. Suppose this is x-axis, an electron is moving along x-axis. Now we consider large number of wave functions. We consider large number of wave functions. That is, we take a large number of waves of different wavelength, and we superimpose them in such a way that they destruct one another at all the points except at one point. And this is one wave. This is again another wave. See here, they are not cancelling. They are in the same direction. The displacement is the same direction. Again here. So in this way, if you take large number of wave functions and superimpose them in such a way that they distract one another at every point except at one point, then what will happen? then psi will be 0 everywhere, and psi will be only a large value of psi. And so if psi is here very high, this means the probability of finding an electron is here, and the electron is 100% to be formed here. The electron is 100% to be formed here, because the electron is no here. Here the wave function have cancelled one another. Here also wave function has cancelled one another. So the electron will be here only. So we have ascertained the position of electrons exactly, accurately. Now, if you attempt to know the momentum of electron, you will be frustrated, because we have ascertained the position of electron using large number of wave functions. And for every wave function, there will be one value of momentum. So there will be large number of momenta. There will be large number of momenta. And so it would not be possible to say what is the momentum of the particle which is situated at this point. So we see that when position is certain, the momentum has become uncertain. Thus, the Heisenberg uncertainty principle has direct bearing from quantum mechanics. The quantum mechanics can explain Heisenberg uncertainty principle, and therefore it can be concluded that the Heisenberg uncertainty principle is due to wave nature of electron. This is all about the second part of quantum mechanics. I think you have understood. In case we have any problem, you are free to ask me questions, you are free to give me queries. You can put queries and I will try to solve them. Thank you very much.